this talk, you have to bear with me a little bit. I mean, obviously, most of us are database people, but I'll actually start very broad, and then I promise you we'll come to databases. Let's go back to 100 years ago, right? At that time, right, there was already electricity, right? Let's say you were a factory at that time that used electricity. At that time, it was still very common that you were actually running your own power generator, right? And then you had somebody managing that and fixing errors of your power generator. And so it actually took quite a while until that got kind of to the state where it is today, right? Today, most people get power through this beautiful standardized interface of a power socket, right? And it's most people relatively cheap, right? It's elastic pricing. You just pay for the amount of, the number of kilowatt hours you're using. And most of the complexity of the of electricity generation is kind of completely hidden from you, right? There's complex electricity and power grids, right? They have to match supply and demand. It's all behind the scenes, right? And you have also these amazing abstractions, right? So basically, as a first-order approximation, every device fits into every socket, and then it just works, right? And so it's actually a pretty old idea, right, to use that kind of, like this kind of utility thinking as inspiration for computing, right? I think McCarthy of Lisp fame was somebody who already was talking about that many decades ago, right? So it's natural to ask, can we have the same thing for computing, right? So that's one way to think about that. And let's talk about this first aspect, right? This low cost that we typically still have with electricity, except in Germany. And so the amazing thing about the cloud computing is that it actually promises to give you a low cost because you have conceptual advantages, right? On the supply side, so on the side of the cloud vendors, they have these ginormous data centers, right? They can presumably get hardware, right, by buying in bulk at much lower cost and get these economies of scale. But they also have, in addition to that, they can also aggregate different consumer workloads from, let's say, different industries, different times of day, right? That's the typical story, and we saw that in the Snowflake case as well. And so this should also give you another layer, kind of, or another dimension with which you can be more optimized and cheaper than if you run your own computing hardware, right, computing resources, right? And so conceptually, these advantages, right, they should lead to lower cost on the first order, like for the cloud vendors, right? And then if you believe kind of in markets, right, you would think that if there's competition between cloud vendors, right, these lower prices should eventually also be reflected to customers, right? So it should be really a great thing for everybody. So that's kind of the cost argument for the cloud, but there's also like a qualitative argument, right, about specialization, right? So and there's this quote by Werner Vogels, who's I believe graduate from University of Amsterdam, and who's been the CTO of Amazon for quite a long time, and a kind of pioneer and advocate of public clouds. And so he calls what usually you had to do if you had to bootstrap your IT infrastructure as, let's say, a growing company. That's not necessarily an IT company, undifferentiated heavy lifting, right? So every company had to do that, right? If you're a startup and your kind of revenue explodes, you have to frenetically kind of scale up your infrastructure and so on. It's very difficult. And the cloud promises you, right, that AWS figures out these difficult things for you, and then all other organizations can just use all the knowledge that Amazon and AWS have learned over the decades, right? So there's also this specialization argument, right? And you could like even more abstractly say that if you look at the history of technology and economics over the last, let's say, 200 years, you can have ever more specialization, right? People used to do a lot of things themselves, and now the economy is like super fragmented, but through the specialization, we learn things and make things more efficient, right? Okay, so there's all these great theoretical advantages of the cloud, right? But now let's compare that with kind of the reality, right? And so on the one hand, the reality is indeed the cloud is taking over everything. And so you find all kinds of plots like these, right? So this is kind of random estimates you find, but you find very similar amounts from many different sources. In this case, it compares data center hardware and software spending with kind of infrastructure spending in the cloud. And in this case, the numbers go up to 2022, right? So by now, if you believe the numbers, it's probably because the cloud revenue is growing so fast, the gap is even larger, right? And so what I want to talk about in this part of the talk is kind of the implications of that, right? And because you have this tremendous market power in a couple of big hyperscalers, this will, of course, really change the dynamics of how we think about server hardware and really change the market. So, and one way to illustrate that is looking at at this plot. So here, this is 10 years of historical benchmark data from AWS, right? And basically what I did here, I always took kind of the cheapest compute instance that you could kind of get, and then this is actually running CPU benchmark on it, and then normalized by cost, right? So this is development of basic compute in the cloud. And you see Intel, right? You see AMD, and then you see this orange line, right? And what is this orange line? Well, this is this graviton line. These are ARM chips, but they're kind of designed and manufactured on order specifically for AWS, and you can't buy them otherwise, right? So at some point, AWS just saw the economics, right? They had such a tremendous scale that they could just build their own chips, right? So not only is the kind of spending of hardware moving to the cloud, the cloud vendors are also building their own hardware, right? So they are taking over basically the hardware markets. And you don't see that not just on the compute side, but for instance, AWS, they also have proprietary virtualization technology with Nitro that basically nobody else has. And they have custom network switches and NICs. So they have super cheap Ethernet, which is, if you want to buy yourself in your own data center, is extremely expensive, right? And somebody from one of these from AWS basically told me that they just got fed up in paying Cisco a tremendous amount of money, and then they built the entire thing themselves, right? And because they have the scale, they can just do it. And at some point, if everybody moves in the cloud, there will be no other hardware market, right? This is kind of the trend that we're seeing at the hardware side. Now, of course, it's not just about the hardware side, right? This is kind of the lowest level you can think of as being the cloud. But the next level is kind of basic infrastructure services like databases, right? And so there's these estimates from Gartner, right, where they compare kind of the market share of the biggest database vendors, right? This is over 5 years from 2017. So this is 7 years ago, right? If you look at that, right? At that time, Oracle was still, if you believe these numbers, the biggest TBMS vendor by revenue. IBM was still pretty large, right? But both of them, right, have been losing a lot of revenue share, right? Doesn't necessarily mean that their absolute revenue is going down, right? And the only line that really grows quickly is of course, that we see here is AWS. And of course, the reason is, again, the cloud. So this adoption of the cloud, not just, of course, if people move to AWS, it's also likely they will move to an AWS-run database system, right? Of course, also to other databases, but many by default will then choose an AWS product, right? And the only company here that, of the old kind of powerful players that managed to keep their market share is Microsoft, because they also have a big cloud business, right? And this is, yeah, you see this, and there's also Gartner estimates. This is a big market, right? $50 billion a year revenue, not like, so this is real money spent by actual customers, and by this estimate, more than half is also in the cloud already. And again, if you look at the growth numbers, this is only going up. And then finally, so that was the infrastructure side, but then you can go, if you go up kind of in this value chain in the cloud, of course, there's all these high-level services. And you're not supposed to see this. This is just a screenshot kind of the AWS website of all the hundreds of services that they have, right? Okay, so if we take all these things together, right, then my claim here that if we just extrapolate this 5-10 years into the future, then we might end up in a world where basically the hyperscale, maybe just AWS, if it continues at the current trends, will completely dominate in the entire world of computing, right? The server hardware, the infrastructure services, and then also based on that, much of the high-level ecosystem of things, right? Let's say AI and so on. So the claim is here, right? If you just extrapolate these trends and think about the underlying economics of them, is that we might end up in a world where we have this vertically integrated monopoly, or maybe an oligopoly, right? Where you have a couple of these big players. And that's, of course, very similar to what we had like with IBM, Big Blue, right? Or maybe Wintel. So maybe we will talk about Big Orange soon, right? So this is kind of because that's the AWS color. Right? And of course, right, from this framing, it's kind of should be obvious that I suspect this is not technologically and in terms of innovation, probably not a good future, because you have then very specific incentives for the hyperscalers, and these incentives are not necessarily towards innovation and technology and so far. Right? So one reaction to that is just say, well, there's nothing you can do, right? I told you, right? These trends are just inevitable, and maybe we just have to assimilate, right? And we just say we just change our research and our kind of development into just adopting into this world, right? And maybe all just do sabbaticals at AWS, and maybe they will tell us something, and there's nothing else we can do, right? As maybe in the 90s, I don't know if it's good, I'm told, right, in the 90s, many people talked about the database world being very stagnating, right? Because there were 3 big database vendors, and everything else was kind of obscure and not very important. So either you worked at one of these 3 database vendors, or you had very little impact on products. Now, that would be a very sad future, I would say, also for academic research, because there's very little things you could do, because these hardware vendors or these cloud vendors could always say, or it's just like these specialized hardware, specialized software stacks. That it's kind of, yeah, it would be a very sad future. So, so luckily my talk is not over. So let me switch tracks a little bit and give you a couple of reasons for hope and why I believe this future is not inevitable. So if we don't do anything, this I think is the default outcome, but there's plenty of reasons for hope. And one of them is coming back to this cost argument. So the theoretical cost argument is that these hyperscalers, they have so many conceptual advantages at the basic hardware infrastructure level, economies of scale and so on, that they by default dominate that world. Now, this is a nice story, but if you actually look at the real numbers, and we'll go through them, you might come to a different conclusion. So what I did here, I looked up kind of more or less arbitrarily what the cheapest AMD instance is, a current generation, kind of a previous generation ARM server with 48 vCPUs or hyperthreads and 192 gigabyte of RAM. And then I did this for AWS and also for Microsoft Azure. And then I'm showing here the what you pay in terms of dollars per month. And what you notice is that basically $1,500, and it's almost exactly for both of them. Okay, so it could of course be, right, because of this market is completely commoditized, and both are very close to marginal cost, and that would be an explanation for these prices, right? Now, but this theory is completely destroyed if you look at other cloud vendors. For example, this Bavarian company called Hetzner. They also offer cloud services, and they offer very similar cloud services at this level that we're talking about. And their on-demand price here is $360, right? So that's 4x of a gap, which is quite a lot. And this is, by the way, not kind of a VC-funded company that's trying to launch up or something. They're profitable company at small scale, so they don't have tremendous discounts when buying servers. So if they can do that, something about the story that I told earlier doesn't add up, right? That it's impossible to compete at that level. Another way to look at this is you just look up for such a server, right? What's the list price on Dell.com, okay? And then you get this number, about $8,000. And you can, again, naively just compare the ratio. How many months do you have to pay for these cloud resources to pay for that server? And then for the hyperscalers, you get 5 months, right? Which seems an awfully small number. Whereas for Hetzner, I would say you get a kind of much more reasonable number of 22 months, right, in terms of the ratio. Now, just one caveat, all these numbers, nobody's really paying, right? So you might that's true both for the list prices of Dell, but also for the so maybe in practice you only pay half of that. But the ratios, they still roughly stand there, right? And so there's quite a surprisingly big gap here at the compute side, right? Okay, you can do similar calculations for storage, right? I'm doing a lot of research with NVMe SSDs, and again, we can look up the kind of biggest service you can rent in the cloud in terms of NVMe capacity. And for AWS, the biggest capacity you get is 60 terabyte here. And for Azure, it's 19 terabytes. And in one case, it's 8 SSDs, and in the other case, it's 10 SSDs. And in this case, let's say because you want to run like a big storage service, let's say we want the cheapest price you can get, so we take 3-year reserve prices, upfront cost, right? So this is the cheapest you get, and then you get to these prices that you can see on the slide. And if storage is your primary metric here, then you see it ends up at $50 per terabyte per month for AWS, for 1 copy on NVMe of your data, and about 100 for Azure. And again, we can compare that with Azure, right? With Hetzner, this Bavarian startup. It's not a startup. It's just a kind of relatively small company, and there you end up at a number of $14. And by the way, the SSDs are also much faster. They are kind of 4 times faster in aggregated bandwidth. Again, right, very similar story, right? And these are not like 30% off, right? But these are integer factors, which is fun fact. People claim S3 is basically for free. It's so cheap, you don't have to think about it. S3 standard is $21 per terabyte. And S3 is, of course, disk-based and super slow. So the funny thing is if you buy SSDs on the kind of at some market rates, right, not AWS rates, and you get your space amplification down by using extreme erasure coding, you could build an S3 based on Flash, right? So taking these things together, right, it seems kind of clear that hyperscaler compute and storage is very far away from being kind of at this commodity level. So it's not true that they kind of, at this point in time, that nobody can compete with them, right? As you see, if you look at these numbers. We can also look at kind of, again, the more high-level things, right, that are important in the cloud. For example, database services, and of course here it becomes more interesting, more complicated to do comparisons. And therefore, the example I like to use, because it's relatively easy, is talking about these query as a service pricing model, because they make it easy to compare numbers. So let's say we have a 1 terabyte data set, and it's stored on some of these object stores like S3, and then we have a query that basically scans this 1 terabyte, let's say compute some simple statistics on that. And then Google BigQuery, they pioneered this very conceptually interesting pricing model where you pay just by the amount of data you scanned. And historically, the price was for a long time $5 per terabyte. So our query, our hypothetical query, would cost exactly $5. Last year, they increased prices to $6.25. Okay. That's why it says $6.25 here for our query. And then on Amazon, they have a very similar service, basically copied in terms of the pricing model, and it's $5 still. And then you can run a similar query also in other cloud-native database warehouses. And we did this with a couple of different ones. And there, oftentimes, you kind of have to start up a cluster, and then you load the data from S3, and then you shut down the cluster. And based on that time, you can also calculate how expensive that cluster would be. And it gives you like a similar range kind of from what we get for BigQuery and Athena. Now, is that expensive? Is that cheap? How do we compare that? So one comparison I like to make is trying to compute a lower bound from EC2. And you could say, for example, that at the very least, right, you have to read this data through the network to some EC2 instance. And EC2, it turns out, has this super fast and super cheap Ethernet. And so if you pick kind of the instance with the fastest Ethernet, then which is 200 gigabits, so you divide kind of this 1 terabyte data that you have to read by this hypothetical network speed of this instance multiplied by the cost, and you end up at 4 cents. Okay. Now, of course, this is not an apples to apples comparison, but I should just point out this is 2 orders of magnitude, right? There's plenty of room here to make this more realistic, this calculation. Again, this indicates we're very far away from the lowest possible, from commoditization at the database level. And to me, that is reason for hope, right? Because if the cloud vendors would offer services at price low, at close to like commodity prices, what you could build yourself, then there would be basically no hope to prevent this vertical integrated dystopia that I mentioned earlier. By the way, this comparison, I think, becomes even more stark at this database query as a service perspective if you look at over time. Because as you see kind of at the top, turns out the prices of these query as a service things don't go down. So you think they implement all these optimizations, and then because of competition, prices would need to go down over time. But this is not what you observe. And as I mentioned earlier, BigQuery prices actually went up. And because at the same time, of course, hardware gets better. And so you expect somehow to prices go down, but they don't. And if you do this lower bound calculation that I had before, you see the gap is actually increasing. Okay. Which is from the economic point of view, the story of competition, right, and people optimizing things and writing all these research papers of databases, on the face of it, quite surprising. So database services are expensive, right? That's what we're seeing, yeah. Okay, but as I said, I think these are all reasons for hope, right, that we can change things for the better. And there's, of course, another reason for hope is the Snowflake story. And I still remember, this was a couple of years, I think, just after they launched. There's a well-known member from the database community who's still working in this data warehousing space, working at one of the big hyperscalers, and he was very confidently predicting that this upcoming startup, Snowflake, had absolutely no chance, right? Because they already offered a data warehouse in the cloud and it's integrated into their ecosystem so people can just click it. How can this startup even have a chance? Okay. And from Alison, we heard already a lot of the kind of innovation that happened at Snowflake and why it actually did take off. Okay. And I think the main one was really that they really redesigned data warehouses from scratch. They rethought them for the cloud, and in particular in terms of the disaggregation between storage and compute, and more elasticity that was standard at the time. There's also, so that basically means a great cloud architecture can still win. Just because a product already exists in AWS doesn't mean that this is the right architecture, as we saw in this example of Snowflake. And what also Alison mentioned is pretty early, not from the start, but pretty early, they also added multi-cloud support. And I think people also more and more realize that maybe it's not the best idea in the world to store all your data and bet basically everything on one particular vendor, one particular proprietary database. And so maybe, and I think that this is exactly what's happening, right? People realize it's kind of dangerous to just completely overfit to, let's say, the AWS ecosystem and, let's say, their specific proprietary database system. And you see that not just like in the example of Snowflake, but you see that in the success of like open storage formats like Parquet and technologies like Iceberg. Okay, so these open data lakes, this is not something that like proprietary database data warehouses really liked, right? Or like basically they're forced to support it because customers are just demanding it. They will not. They realize that this vendor lock-in is kind of a dangerous thing. Right? So to summarize, right, from my perspective, these are all reasons for hope that disruption is still possible. So because we saw, it's not true that they offer hardware or virtualized hardware as cheap as possible. There's a big gap between what they charge for and what is possible. The same is true for database services on top of that. So there's another big factor on opportunity. But then these are just kind of the cost side, which is, as Snowflake's story also told, maybe not even the most important things. The most important thing, I think, is that people don't want to be reliant on a single vendor. They want multi-cloud support, and they also like interoperability in broader sense, and also in the data lake sense is kind of an important thing. So if that is so, there's all these opportunities that I claim, okay? Why isn't there, for instance, why is there no Snowflake for OLTP, okay? And so I've been working the last years, and Peter mentioned it, on a storage engine called LeanStore, and it's kind of was kind of designed for a single server, right, in kind of an on-premise world mostly. And the last couple of years we started thinking, okay, how would we move this thing to the cloud? What would you have to do? Okay? And I think this will be kind of an interesting case study that will maybe explain why this disruption that's in principle possible, as I hopefully made a case for, is hard, and then also tell us how we can hopefully make it easier. So, turns out if you, well, I could give an entire talk about this slide basically, but turns out kind of the summary is that if you want really a proper cloud-native OLTP system, then you need not just a very fast OLTP kind of server, and this is kind of the research that I've personally done in the last years. That in itself is, of course, a very big project. But the first thing that you notice is at some point you need to write some durable write-ahead log entries. And where do you put them? Okay, it's not so clear. I think the best solution actually is, and this was actually proposed by Microsoft in the Socrates paper, is to have a separate service that has very specific requirements in terms of durability, latency, specifically for this use case of just shipping a write-ahead log entry there, and then it's acknowledged to be durable, and then it can be staged to some cheaper service and so on. None of the existing cloud services that are ready to use, that you can just pay for and that are hosted by other people, actually offer that. Okay? This thing exists in many different companies, many different databases, but everybody implements it themselves. Now, the same is true for the storage layer. So with Snowflake, we learned, right, that they're using S3, and for analytics use cases, this works. Now, it turns out for OLTP use case, you can't use S3 because latency are just so terrible. Okay, so now you can read the Aurora paper and learn how they implement their distributed page server. And it turns out it's not so trivial, super complicated. It needs to be multi-tenant to not just be expensive, but actually to reap any of the benefits of the cloud. So that's super hard. And then finally, if you run in cloud, everything is a service, right? So somehow we also, Alison was also talking about this, some kind of control plane. Basically, every cloud service needs a control plane. And that's in itself, again, a pretty complicated piece of technology. And each of them, right, or almost each of the three of them are highly complex and distributed systems. So we now have to build these super complicated database systems, and then also these super specialized distributed system components. And these components need to be highly available because they're multi-tenant. So if one of them goes down, then maybe all your customers will suffer. You need high durability, and everything is multi-tenant. So security is also a big issue. Okay, so that seems like pretty hard. Okay. Now, my claim here a little bit is that, so I'm trying to build this cannon, okay? So this OLTP system. And then you realize, well, to build this cannon for the cloud, you need wheels. And then you go into the side quest, like this log service of building, prototyping all kinds of wheels. So somehow we're reinventing the wheel, and turns out that almost every database startup goes through this transition, right? So they figure out, I need this, I need that, and then each of them is super complicated. And so my hypothesis here a little bit is that what we're missing is some new abstractions, right? So most of the abstractions that you have in the cloud, and also in terms of our thinking, they still come up from a pre-cloud world. And some of these examples that I showed with this log service, it seems completely obvious to me after thinking about this couple of years. And for many people who know this space, also to them they agree that you need this logging service. And so you can ask, why doesn't it already exist, like as a ready-to-use service? Now, it turns out these things are hard to monetize. So if you start a startup on this offers this logging service, it's like super mission critical. Nobody will trust you, and it's also very niche. You only have 100 customers in the world. So somehow they don't, for this reason, don't exist. You have more high-level things, but then everybody needs to build an entire stack of these small components. By the way, fun fact: there's a talk on Amazon S3. And they are bragging about their scale, and they at some point mentioned that S3 itself consists of 300 microservices, right? So, and they use that as bragging, but I would say this also implies that, first of all, that the layering is not right, and secondly, that it's almost impossible to change anything there. So if they switch from disk to flash, they just have to do a complete restart, and they did that. And as far as I know, the new product has nothing to, the flash-based one has nothing to do with the old one. Okay, so back to my claim here. I'm claiming here that these low-level building blocks that will make it realistic to build new services to be able to disrupt the current situation, they just don't exist because they're hard to monetize. And so everybody implements them again and again. And so there's, for instance, a lot of Aurora clones, and every one of them realize they need the log service, and they do some terrible workarounds. And so the consequence is that because it's so hard to build and run a cloud service, and because the complexity budget is limited that you can do, right? It's already hard to build an OLTP single node system, and then you have to do all these other things, and they just use suboptimal designs which often lead to high cost, and then all these gaps theoretically that I showed you, they shrink, right? And the system is just inefficient and expensive. So how do we get out of this mess, right? So actually I told you a lot of maybe sad things, but actually this is supposed to be an optimistic talk. And so we all know, right, the Borg are a very formidable opponent. So how do we defeat them? So my current theory is the following. So we just have these to follow these steps, right? Step number one is we can only rely on the least common denominator, and that is virtualized servers. Okay, so this is what we'll do, and maybe you have a very, very lightweight abstraction over it, so you can start a virtual server and stop it, and that should be pretty easy to run in all kinds of clouds, okay? Now, based on that, we have to build completely new building blocks, including storage services, because the existing storage services are not 100% compatible between the different clouds. And so that includes this logging service that I mentioned for OLTP. It includes basically things like S3 now optimized for flash because disk is basically close to dead anyway. I think it would also be great if we have some general control plane abstraction that would make it easier to run and monitor and do monitoring and billing for multi-tenant cloud services. And it would be also amazing to have actually a completely compatible OLTP cloud service that runs in all the clouds, because this OLTP service is, of course, also a critical component within the control plane. Or that's one way to build a control plane, having this standardized OLTP service. Okay, and then I don't just want to build one OLTP system for the cloud, but I think the amazing thing, if you do it that way, you expose all these low-level building blocks, and not just the OLTP system. Right now, all these Aurora clones, they expose an OLTP database, but they don't think in terms of this layering and exposing these low-level building blocks. And I believe if we have these new building blocks, and that should make it easier to create kind of completely new abstractions that don't exist at all at the moment, because it's just so hard. Everybody does this real reinvention. And the concept of that could be really awesome. So first of all, if you followed my steps, right, we're only relying on virtualized servers. So this is something you can run in any cloud, okay? Because all the like mid-level services, like storage and so on, is then completely compatible across different clouds. So you have whoever runs in this ecosystem will run anywhere, okay? And then actually, just the hardware itself should get commoditized. And then these large gaps that we saw in comparison heads now with AWS, in the medium term shouldn't exist anymore. And then hopefully this will also make it easier to create new cloud primitives and also high-level services by exposing these low-level building blocks that my hypotheses are currently missing. And I'm a database person, right? So I know this for the OLTP use cases, but I'm sure many other domains you have very similar things, right? That you're building a server for X, but to build the server for X, you would actually like to have some other primitive services Y and Z. And so this is basically what we started doing and working on. So this is all ongoing work. And again, this comes from this lean store thinking where we realized, well, actually to move lean store into the cloud, we have to build these components. One of them is this log service, right? And then it has very specific characteristics, very low latency, very high durability. But on the other hand, storage capacity is not an issue because you just batch these writes together. And then you then move it to these page servers, which if you build them for Flash from the start, you can get very different characteristics, and hopefully you're still pretty close cost to S3. And I also envision a layering there. You have a low-level kind of paging service only with out-of-place writes that actually does very little, and then database systems can use that directly, but then you can layer this based on a more conventional storage service that offers you more high-level typical interfaces. And again, right, I think these are just an example. I think you can extend this idea to other domains, but this is, I think, the first, to me personally, makes most sense because I've worked on OLTP. And of course, there's many open questions, right? What other abstractions can you come up with? And so this idea, right, can you somehow make the control plane itself, can you generalize across different services? I think that's a very interesting question, okay. So let me summarize, right? I think whether we like it or not, right, the cloud is changing computing, right? It's here to stay, so we have to kind of think hard about how to use it and also how to shape it. And on the current path, it looks like the hyperscalers are just becoming vertically integrated monopolies, and which would be, I think, a sad outcome. But on the other hand, I also showed you reasons for hope and why I think disruption is, at least now, still possible. There's still these big gaps, right, in terms of the compute cost and infrastructure database cost, basically. And then people also more and more realizing that maybe they shouldn't get too dependent on a single proprietary cloud. And then the second part was more speculative, right? So my path that I see to a better world is to make it easier to build cloud services and to make it easier to build multi-cloud services. And I think that could be actually the actual vision of the cloud that I started with, right? The current path, it seems like is not what we want. So thank you.